Let's discuss the Gibbons-Hawking-York boundary term in general relativity. General relativity is governed by the Einstein-Hilbert action, which is an integral over the whole of the spacetime manifold of the Ricci curvature. Now we might have a manifold which is non-compact, perhaps of infinite volume, and it could be difficult to evaluate this action, which might be infinite. So it's natural to ask for an infrared or large volume regularization. So we can imagine that we should introduce a cutoff on our boundary, a cutoff on our manifold. And now the manifold has a boundary. But then a natural question becomes, what are the boundary conditions and how do we define a good variational principle? A good variational principle will be one in which, if we satisfy the equations of motion and the boundary conditions, then the action is extremal. So now, the first guess at good boundary conditions is that we fix the metric G alpha beta at the boundary of our manifold. And therefore, the variation of the metric at the boundary will be 0. Now, it's good to make a footnote here. It may be better to fix the conformal class of the metric, so the metric up to a scale factor, as well as the trace of the second fundamental form, i.e. the trace of the extrinsic curvature. And the reason this may be better is because it guarantees that the differential equation in the Euclidean has an elliptic nature, while the Dirichlet boundary conditions that we are going to take do not necessarily have this property. But anyway, we shall continue in traditional fashion and study the Dirichlet boundary conditions. So we do fix the metric at the boundary. Now, we should now check the variational principle and whether it's consistent with the boundary conditions. To that end, we calculate the variation of the Einstein-Hilbert action times 16 pi g Newton on a manifold with boundary. The result of this calculation is that we find the integral over the manifold, and then basically the Einstein equations for the Einstein tensor times the variation of the metric but we also find an extra term. So let's call this first term 1. But we also have a second term, which is the integral over the manifold G alpha beta delta R alpha beta square root minus G for Minkowski metric e to the fourth x. So now, why don't we usually talk about the second term? It's because it's a total derivative. So in what sense is it a total derivative? Well, we have delta r alpha beta, g alpha beta is equal to the variation of a metric, covariantly derived and traced, where this vector is related, or where the variation of this vector is related to the variation of the Christoffel connection symbols. But anyway, since it is a total covariant derivative, one can apply Stokes' theorem. It says, in the form that we needed, that the integral over the manifold of this total derivative, more generally any total derivative, is equal to an integral over the boundary of the manifold. So if the manifold has no boundary, our variational principle is automatically well defined. But if it does have a boundary, then even if we set the Einstein equation or the Einstein tensor to 0, we could still have a non-zero variation of the action. Now, using the variation we just computed, as well as Stokes' theorem, as well as the equations of motion, we find that the variation of the Einstein-Hilbert action becomes minus the integral over the boundary epsilon, where epsilon is nothing but, right, should introduce the symbols. Epsilon is nothing but the sign of the vector n, which could be time-like or space-like. We have coordinates y on the boundary. X were coordinates on the manifold M, and h is the metric induced on the boundary. So we have some embedding equations, and with those we can pull back the metric on the full space to a metric induced on the boundary, and this we call h. And then finally, and most importantly, the vector m is a unit vector, normal, that is to say orthogonal to the boundary of the manifold M. So with all this being said, we can compute the variation of the connection coefficient, and then we find that the variation of the Einstein-Hilbert action equals this expression. So now it should be noted that even if the equation of motion is satisfied and the boundary conditions are satisfied, then still delta S Einstein-Hilbert could still be non-zero if the variation of the metric on the boundary has a non-zero derivative, which is possible. We only fixed the value of the metric on the boundary. So therefore, we need a new boundary term in the action for the variational principle to be well defined. In other words, to cancel the remaining variation. That term is the term we're after. It's the Gibbons-Hawking-York term. And it's equal to 1 over 8 pi g times the integral over the boundary now of the manifold, d to the third y square root of mod h times epsilon times the extrinsic curvature trace k. So now we should compute the variation of this action. And to compute it, we compute the variation of k, which is nothing but the variation of the covariant derivative of the normal vector, which, using various constancies, is nothing but the variation of h alpha beta contracted into n alpha derived with respect to beta minus a connection coefficient, which, using the constancy of h, constancy of n, and so on, is nothing but minus h alpha beta times, again, the variation of a connection coefficient, which again can be computed under all the assumptions necessary to be the derivative of the metric variation. Using this, one finds that 16 pi g Newton times the variation of the Gibbons-Hawking-York boundary term is equal to, well, the 2's cancel. The boundary manifold remains fixed, as do the coordinates, as does the boundary metric, as does epsilon and n. So we only have the variation of the extrinsic curvature trace, which is equal to h alpha beta delta g alpha beta mu and mu. Now, we should compute the variation of the full action, namely the Einstein-Hilbert action, plus the Gibbons-Hawking-York term. We found a first term, a bulk term proportional to the equations of motion. Then we found a second term, which is written here, from the variation of the Einstein-Hilbert term. We found a boundary term. And then we should also vary the Gibbons-Hawking-York term, and we found this variation. And the point is that these two extra variations now cancel. Therefore, with the Gibbons-Hawking-York boundary term, the variational principle for general relativity with Dirichlet boundary conditions is well defined and gives rise to Einstein's equations of motion. It's wonderful. So why is this important? Well, the boundary term will be important for very important aspects of general relativity, like computing the mass of a particular configuration, but also, for instance, for computing black hole entropy, particular the semi-classical value of the black hole entropy, will depend on the Gibbons-Hawking-York term, and also for the composition of path integrals in Euclidean quantum gravity to be well defined. So far from being an afterthought to the Einstein-Hilbert action, the Gibbons-Hawking-York term is quite crucial for the whole of general relativity.